Hello students, welcome to the course on network theory. We shall continue our unit on two-port network, and today's topic is the applications of our H parameters to real world problems and solving some of the numericals. Now we move from our general two-port network theory, which is discussed in the last lecture, to one of the most important practical applications, that is the transistor amplifier. In real electronic circuit, especially the BJT amplifiers, we require a model that connects the input voltages, input current, output voltages and output current. This is where our hybrid parameters or H parameters becomes extremely useful. So, two-port interpretation of this is the following two-port interpretation of our transistor. In this diagram, the transistor amplifier is treated as a two-port model. Okay. So this is the transistor amplifier, which we assume this as a two-port model. Here the input side is the base emitter region and the output side is the collector emitter region. So instead of analyzing the internal transistor physics every time, we try to use this transistor as a black box model based on the measurable parameters. This makes the circuit design significantly easier. So, if you try to see in the input port, that is at port 1, we define V1 as the input voltage and I1 is the input current. Right? The biasing resistances R1 and R2 set the operating point, but for small signal analysis, we focus on incremental behavior around the Q point. This is important because our H parameters are small signal parameters, not the large signal. Now coming to the output port, at port 2, we define V2 as output voltage and I2 is the output current. The collector resistance RC and the load resistance RL influence the output characteristics. And here RC and C and the load resistance RL is generally influence the output characteristics of our transistor. So the capacitor shown is the coupling capacitor, which tries to block the DC and allows the AC signal transfer. So the signal flow from input port to the transistor amplification, then for the output signal. This amplification occurs because a small phase current controller controls a large collector current. So H parameters or mathematically captures this particular behavior. What are the H parameters we have? H11, H12, H21 and H22. So this H11 is the input impedance. These parameters actually represent how much input voltage is required to produce an input current. Right? So in simple terms, it tells us how difficult it is to drive the transistor input. So it is measured in ohms and represented as base input impedance, looking from the into the transistor. Next is our H12. This is a reverse voltage gain, which we have discussed in the last lecture. This parameter shows the feedback effect from the output port to the input. So in most practical BJTs, this value will always be very small. So we define or we generally assume that my H12 will be approximately equal to 0. So this simplifies the amplifier analysis significantly. The next is H21. It's a forward current gain. So this is an important parameter. Actually, here it tries to represent the current amplification capability of the transistor. In BJTs, these correspond to beta or HFE. So this the parameter determines how strong the amplification is. So this amplification is generally varies from 50 to 300 for BJTs, and the forward current gain is otherwise called as short circuit current gain. And the final one here, H22, is the output impedance. So this parameter describes how my output current depends on the output voltage. It relates to early effect, your output resistance of the transistor. So it is measured in Siemens and the value of H22, a small value of this H22 means a good amplification behavior. So hybrid equation meaning is that it's a mix of voltages and current variables. That is the reason we call these parameters are hybrid parameters. So they try to combine the input voltage dependence, the output voltage dependence, and the current gain behavior and the loading effect. This makes them extremely practical for circuit engineers. So we can see that this H parameters model allows us to predict the amplifier gain, calculate the input impedance, estimate the output voltage, and understand the feedback effect without solving the complex transistor physics equations. So this is why they are widely used in low frequency amplifier design. Now that we understand how H parameters model a transistor amplifier, let us explore where else this modeling approach is used in our real engineering practice. This will help you appreciate the engineering relevance beyond this particular theoretical class which we have discussed in the last lecture. So the other applications here is first is your transistor amplifier design. So in multi-stage amplifier, each transistor stage can be represented using H parameters. This allows us to calculate the overall gain using a systematic circuit analysis. So this is especially useful in analog communication systems, audio preamplifiers, instrumentation amplifiers, for gain analysis or small signal modeling of any BJT amplifier stages. And another application here is the analog IC design. In integrated circuits, thousands of transistors are interconnected. Small signal models based on hybrid parameters help designers to predict what is the voltage gain, what will be the bandwidth, and what is the stability. So this forms the basis of our analog VLSI design. The third application here is the audio electronics. So in audio systems, signals operate at low frequencies. So H parameters models provide accurate prediction of amplifier performance in this particular range. So they help in designing the tone control circuits, audio power amplifiers, and microphone preamplifiers. And the next application we have here is the sensor interface circuits. Biomedical and industrial sensors produce extremely big signals. So H parameters modeling helps in designing the signal condition amplifiers, low noise amplification stages, precision measurement circuits. So this is the critical in instrumentation engineering. Now the next application here is the discrete circuit design. So when engineers design the circuits using individual transistors instead of ICs, H parameters simplify this manual analysis. That is, they allow us to calculate the gain and we allow us to find the impedance matching and estimate the stability. This is very important in prototype circuit design. And the other thing where we can apply is in the electronics education. Finally, these H parameters plays a very major role even in the teaching. They provide students with conceptual understanding of transistor behavior, mathematical model skills, bridge between the theory and practical design. This is why they are still taught in even at the age of simulation tools. So overall, the H parameters are a practical engineering model language for transistor circuits. So they help engineers predict the real circuit behaviors using simple measurable quantities. Okay. So these are the some of the applications of our H parameters for real world problems. So now we shall discuss or solve some of the numerical problems. Now let us solve this numerical, and this is the first numerical of this particular lecture. Right? What we need to do? We need to determine the H parameters for this particular circuit, and we need to identify whether the circuit is reciprocal or symmetrical. So as we discussed in the last lecture, how do we need to do? We can apply any of the mesh analysis, nodal analysis, circuit detection technique, or the conventional step-by-step of following the H parameters. So let us start with following the conventional way of solving this particular circuit. Okay. So as of then, what are the things we are going to have? What are the equations? So we are going to have V1 equal to H11 I1 plus H12 V2. What is the second equation? Second equation is I2 is equal to H21 I1 plus H22 V2. So these are the two H parameter equations. What are the two case studies we are going to have? Two cases are case 1 when we make our V2 equal to 0. When we make our second port short, we are going to compute two parameters, namely H11 and H21. In the second case, case 2, we are trying to make I1 equal to 0. We are trying to open the input port. As a result, we are going to compute the other two parameters, namely H12 and H22. Okay. So if you observe these two equations, you can see that we are having two independent terms here, I1 and V2. So there should be a current source towards input port, and we should have a voltage source at the output port. So let us draw here. We are having a current source. This is my I1, and we have a voltage source that is V2. This is my V2. So let us take this case 1 by shorting this particular second port, that is removing this voltage source and short circuiting this particular two terminals, by which we can say that V2 is equal to 0. Let us redraw the particular circuit. Here we are having 10 ohms, 300 ohms, 50 ohms, 100 ohms and 10 Vx is a voltage dependent voltage source. What we have done? We have shorted the second port. And we are activating the current source. So we have deactivated the voltage source, we have activated the current source, that is I1. Okay, and if you observe, this is a short circuit, so we are going to have a current I2. Okay, so what we need to find? We need to find H11, which is equal to V1 by I1. And what is the other thing? We need to find H21, nothing but I2 divided by I1, right? So H11 is nothing but V1 by I1 and H21 is nothing but I2 by I1. So these are the ratios we need to find, or these are the parameters we need to find. So let us apply our nodal analysis at this particular point. So if we try to apply our nodal analysis over this particular point, we are going to have I1 equal to, here this I1 current enters comes to this particular node and get distributed with these two branches. So the current flowing through this particular branch and the current flowing through this particular branch. So what is the voltage across this particular branch? It is Vx and the resistance is 100. So it is Vx by 100 ohms. This is the current flowing through this 100 ohm resistor. And what is the current flowing through this resistor? Is the voltage at this particular point is Vx and the voltage at this particular point is 0 as it is grounded. So the current flowing through is the potential difference between these two nodes divided by 300, the resistor here, plus Vx minus 0 divided by 300. So my I1 is equal to 3Vx plus Vx by 300. So it is equal to 4Vx by 300. So we can write Vx equal to 300 by 4 Vx, which is equal to 75 Vx. Okay, sorry, 75 I1. It is 75 I1. Here also this is 300 when it goes to here, 300 into I1 by 4. So it is 300 by 4 I1. Not this will be I1. Okay, let us assume this is equation 1. But if you try to see that this particular loop, so we are going to have the voltage V1 created across this particular terminal. So how can we write? So my V1 is equal to the voltage drop across this resistor and the voltage drop across this particular resistor. That is V1 equal to 10 I1 and voltage across the resistor is Vx, right? So why we are trying to write this equation? Because we need to have a relationship between V1 and I1. Already we have a relationship between Vx and I1. So if you try to substitute Vx equal to 75 I1 over here, we are going to get the relationship between V1 and I1. So my equation becomes V1 equal to 10 I1 plus 75 I1. So if you try to add these two, we are going to have V1 equal to 85 I1. So my H11 is equal to V1 by I1 is equal to 85. It is ohms. Now let us apply the nodal analysis at this particular node 2. So if you observe, we are having an incoming current, that is I2. This I2 is getting divided among two parts. So if you try to apply our nodal analysis, the incoming current equal to the outgoing current, then we are going to have I2 is equal to what is the current flowing through 50 ohm? Is nothing but the potential difference across 50 ohm, that is 0. Here what is the voltage? Here this is 0 means this will be minus 10 Vx. So 0 into 0 minus of minus 10 Vx divided by 50. So we are going to have 0 minus of minus 10 Vx divided by 50 plus what is the current flowing through 300 ohm? It is similar that the potential difference across this resistor divided by the value of it. What is the potential difference? It is 0 minus Vx divided by 300. So the 0 minus Vx divided by 300. So my I2 can be written as 10 Vx by 50 plus minus Vx by 300. Okay, so but what is the thing we require? We require the relationship between I2 and I1. So if you see here, the left hand side we have I2 and the right hand side we have Vx, but we know that Vx is equal to 75 I1. Okay, now let us substitute over this equation. So before going to that, let us simplify it. My I2 is equal to I2 will be equal to multiply and divided by 6. So we are going to have 60 Vx minus Vx divided by 300. So my I2 is equal to 59 Vx divided by 300. Now try to substitute Vx equal to 75 I1. So we are going to get 59 into 75 I1 divided by 300. So if you can see here that it is 75 1 ja, 75 4, 4 1 ja, 4, 14, 4 1 ja 4, and 16.75. So my I2 is equal to 14.75 I1. So if you try to take the ratio, my H21 will be equal to I2 by I1, which is equal to 14.75. This is my H21 and this is my H11. So this is the case 1. By shorting the second port, that is by making V2 equal to 0, we were able to compute the two parameters, that is H11 and H21, and we got H11 as 85 ohm and H21 equal to 14.75. Okay, this is a unitless quantity because the ratio of amps to the amps. Okay. Now we shall go for the case 2. So in case 2, what we need to do? We need to make I1 is equal to 0. So which we have discussed here. So in case 2, if we try to make I1 equal to 0, we will be able to compute H12 and H22. So what is my H12? Is nothing but V1 by V2, and H22 is nothing but I2 by V2. So these are possible when we make my I1 equal to 0 and I1 equal to 0. So what we are trying to do? So for the given circuit, we are trying to make I1 equal to 0, nothing but we are trying to deactivate this particular source. So if we are trying to deactivate this source and we are keeping this particular voltage source V2 as it is. Okay, so let us draw or complete this particular circuit. So this is the condition where we are going to have I1 equal to 0, but we are having V1 plus minus, and we have I1 equal to 0. Now if we try to have the same voltage source as it is, what we are going to have? We are going to keep V2 as it is. So as a result, we are going to have current I2. So I1 and V2. So we are activating the voltage source V2 and deactivated the current source I1. That is, we have opened the first port. Now our objective here is to find the relationship between V1 and V2. V1 is here and V2 is over here. And the other thing is we need to get the relationship between I2 and V2 itself. Okay. Now as I1 is equal to 0, now let us redraw this particular circuit. So how my circuit will look like? We are going to have a 300 ohm resistor here, and we are having 100 ohm resistor here, and we are having 50 ohm resistor here. Here we are having a dependent source. This is minus plus, and this is the point where we are going to have the voltage source V2 plus minus V2, and this is the current I2, and this is V1 plus minus, and which is also equal to Vx. So if you observe here, my V1 is equal to 10I1 plus Vx, but I1 is equal to 0. So my V1 is equal to Vx, right? So my voltage across this 100 ohm is nothing but Vx, nothing but here V1, as we have opened the first port. Now what we need to do? We need to bring the relationship between V1 and V2. So if you observe carefully, we can see that my V2 is nothing but voltage across 300 ohm plus voltage across 100 ohm. So let us write here. My V2 is equal to voltage drop across 300 ohms plus voltage drop across 100 ohms. Okay. So what we require? So here V2 is getting divided. So if I want to find what is the voltage across 100 ohm, we can apply our voltage division rule. So voltage across my 100 ohm is nothing but Vx, which is also nothing but V1, which is equal to its own resistance 100 divided by total resistance, that is 100 plus 300 into total voltage V2. So if you observe here, we got the relationship between V1 and V2. So V1 is equal to 100 divided by 100 plus 300, it is 400 V2. So V1 is equal to 1 by 4 V2. Here get divided or cancel each other. Okay. So but what we require? We require V1 by V2. So my V1 by V2 is equal to 1 by 4. V1 by V2 is nothing but H12. So my H12 is equal to V1 by V2, which is equal to 1 by 4. Now we shall find the remaining parameter, that is H22. So let us redraw the circuit in the next slide. So we are having a V1 here plus minus, and we are making this I1 equal to 0, and we are activating this particular source. We are keeping this source as active, which is nothing but V2, and we have a current I2. Now our objective is to find the ratio of I2 by V2, that is my H22, when my I1 is equal to 0. So for this, let us apply our nodal analysis at this particular node. So your incoming current is I2, and let us say we are having a current Ix in this particular branch and Iy in this particular branch. So my I2 is nothing but Ix plus Iy. So how do we find this Ix? Ix is the current flowing through 50 ohm. So how do you find the potential difference across these two terminals? So what is Ix? Ix is a current flowing through the 50 ohm branch. So how do we write? It's a voltage across or potential difference across these two terminals divided by the value of that resistance. So as the current Ix is going from right to left, my V2 is higher potential compared to the voltage at this particular node. So my Ix can be written as V2 minus the potential at this particular node is how much? If we assume that it's a ground potential, then this should be minus 10 Vx. So we are going to have minus 10 Vx. So V2 minus of minus 10 Vx divided by the value of this resistance 50 plus what is Iy? Iy is the current flowing through this particular branch. So if you observe here, my I1 is equal to 0. As a result, my 300 and 100 ohm are connected in series, which is as shown here. So what is the current flowing through that particular branch means nothing but potential difference across those two terminals, that is V2 minus 0 divided by 300, right? So it is equal to V2 plus 10 Vx divided by 50 plus V2 divided by 300. So if you observe, we have I2 in terms of V2 and Vx, but what we require that only the relationship between I2 and V2. So we need to eliminate this particular Vx. How do we eliminate? We need to bring some relationship between Vx and the V2, so that we are going to have only V2 terms in the right side. Okay, so if you observe the previous diagram here, I'm going to redraw this one here. So this is your 300 ohm and we have here 100 ohm resistor, and this is Vx, voltage across this, and we have a 50 ohm resistor and we have a dependent source of value 10 Vx, and here we are having the port, that is V2 plus minus. So V2 is applied across these two nodes. So voltage V2 is getting divided among the 300 and 100 ohm resistor. But what is the voltage across 100 ohm? It is Vx. So by applying our voltage division rule, we can find the value of Vx as the value of resistance across it, that is 100 divided by 100 plus 300 into V2. This Vx is nothing but 100 divided by 400 V2. So Vx is nothing but V2 by 4. So if you try to substitute that Vx equal to V2 by 4 here, what we are going to get? Sorry, it is V2 by 400. This is V2 by 400. As these two resistors are connected in series, the current flowing through this will be I2 equal to 300 plus 100, it is 400. So my I2 is equal to V2 plus 10 into what is Vx? It is V2 by 4 plus divided by 50 plus V2 by 400. Okay. So let us multiply and divide by 8. So we are going to get 8 V2 plus 20 V2 plus V2 divided by 400. So 8 5 is 40, 400 plus here we are having 400. So that is the reason we have written in this particular way. So my I2 is equal to 28 plus 1, 29 by 400 V2. So my H22 is equal to I2 by V2. So we can write that my H22 is equal to I2 by V2, which is equal to 29 by 400 mho. So 29 by 400 mho. So this is my the other parameter H22. So finally we got the fourth parameter, that is H11 as 585 ohms, H21 as 14.75, H12 it is 0.75, and H22 is 29 by 400 ohms. So let us stop here for this lecture. In the next lecture, we are going to find the interrelationship between different parameters. Thank you.